Hello guys, Assalamu alaikum. Today I'm going to share the Navier-Stokes equations today. So um, if um, consider consider that a lake. This is a lake. Oh, sorry. So this is a lake is flowing. The water is flowing in the lake. Okay. So if I gave you the velocity and pressure, that U is the velocity and the pressure is P, then it at every single point, here. So would you be able to predict how the lake flows over time? So this question points to the Navier-Stokes equations, a set of equations that can describe any fluids you can think of, from water to air, air to honey, and so on. Okay. So what is that equation? That equation is the grad U is equal to 0 and rho du by dt is equal to minus grad p mu grad square u plus f. This is the Navier-Stokes equation. So you might have heard of these equations because they are a part of Millennium Prize problems, a collections of 7 incredibly important and difficult mathematical problems. So what are the 7 mathematical problems? The mathematical problems are the Young-Mills and match gap, Riemann hypothesis, P versus NP problem, the existence and smoothness of Navier-Stokes equations, the Hodge conjecture, the Poincare conjecture, the bridge and Swinnerton Dyer conjecture. So a correct solution to any of these 7 problems is awarded $1 million cash prize. This is very valuable. So today let's talk about these particular problems. The number 4, the existence and smoothness of the Navier-Stokes equations. So today's topic is the existence and smoothness of Navier-Stokes equations. Okay. So the Navier-Stokes equations are probably one of the most important partial differential equations for fluid mechanics. They are used to forecast the weather, model airplanes and rockets, and predict water currents. So despite the extensive uses, there's still not that much we about these equations, mathematically speaking. But first, let's talk about what these equations actually are. For the purpose of this video, I'm going to make a few assumptions about the fluid we are talking about. So the assumption of this video, assumption of this video is: number 1, the fluid is Newtonian. And number 2, the fluid is incompressible. Number 3, the fluid is isothermal. Okay. So the first assumption is that the fluid is Newtonian. There are a really good answer on the stock exchange that explained what it means for a fluid to be a Newtonian. But let me just summarize it for you. That when we call a fluid Newtonian, it means that the rate at which we apply some shear stress has no effect on its viscosity. Okay. So I'm going to draw a graph, number Newtonian. So this graph is, here is the viscosity and here is the shear rate. Okay. So Newtonian is this this flow. So here is no shear stress effect. Okay, on this viscosity. An example from this answer on stock exchange is ketchup, like um, সসের বোতল। সসের বোতলে কি হয়, যখন আমরা সস ঢালি তখন দেখা যায় যে অনেক সময় সস বের হতে চায় না, যখন আমরা ঝাঁকুনি দিই তখন আমার সেই সসটা বের হয়ে আসে। So when we have difficulty removing ketchup from a bottle, something we all do is heat the bottom of the bottle, and the ketchup comes out with easy. So looking at the ketchup shear rate versus viscosity graph, we can see that heating the bottle, which increases the shear rate and decreases its viscosity, which lets the fluid out. Okay. And number two, the second assumption is that the fluid is incompressible. বাংলায় যেটাকে বলে কি অসংকোচনযোগ্য. It means exactly what you think. If I compress the fluid that is at pressure, there is no considerable variation in the volume of the fluid. Okay. যদি এটা আমার সংকোচনযোগ্য হয় তাহলে কিন্তু আমার এই ন্যাভিয়ার-স্টোক্স ইকুয়েশনটা কাজে লাগবে না, অর্থাৎ এটা ইনকম্প্রেসিবল হতে হবে। And the last assumption is that the fluid is isothermal. Okay. So this just means that the fluid flows, there's no loss or gain of heat. And this takes us to the Navier-Stokes equations. As daunting as they may seem, they're actually based on quite well-known physical properties. Note that when we talk about fluids, we typically talk about an infinite decimal volume of fluid. And so we are trying to describe the motion of each individual molecules there rather than the fluid as a whole. So this first equations right there, this first equation right here tells us that mass is conserved within the fluid. Okay, the mass is conserved within the fluid, and the operator here is called this operator is called what? This is divergence. Okay, divergence of a vector field, and the vector field in this case u. The vector field is u. This is the vector field. A vector field is what we get when a vector field is what you get when you assign every single points in a space to a vector. Okay. So the divergence of a vector field is an operator that tells us how much a point tends to the divert vectors away from it. Okay. So consider this vector field. It appears that vector seems to be moving away from the origin. This indicates positive divergence. So positive divergence, divergence of f is greater than 0. This is positive. The graph will be like and the negative divergence is less than 0. The graph will be like okay. So similarly, the vector field seems have a vector that flows into the origin. This indicates negative divergence. Numerically, we write the divergence as a dot product between the gradient vector and its vector field. So in terms of fluid, the divergence of a vector field indicates how much and how little of points acts as a source of a fluid. If we imagine water in some area, it impossible for the water to simply disappear. It could either change forms, but mass is never destroyed. So, and thus the divergence across the fluid has to be 0. And hence the first Navier-Stokes equations is gradient of 0 gradient of u is equal to 0. And now the second equation is rho du by dt is equal to minus grad p plus mu grad square u plus f. So if you remember, Newton's second law tells us that the sum of forces acting on a body can be written as its mass times the acceleration. Considering this for a single molecule of fluid, let's see how we can derive the second Navier equations. First of all, since we are considering each individual points, let's replace the mass with density that we know from Newton's law that F is equal to ma. So if we first are going to replace the m with the density, rho. The mathematical reason behind doing this is that to consider each individual points, we have to divide the volume, and mass by volume is equal to density. So we know that m is equal to rho divided by v. So here v is 1, sorry, m divided by v, and v is equal to 1. So the rho is the m, okay? And let's consider acceleration is a. So a is equal to du divided by dt. So a is du divided by dt. So here is the equations AMA. So a quick side notes that you might see that this part written as um, del u by del t plus u gradient of u. This is the chain rule. This is essentially same things. When we expand du by dt, we will use the chain rule, which gives us the other expression. Now we need to consider what are all the forces acting on this molecule of a fluid. We can break this down into internal forces, which are forces exerted by the molecule of the fluid itself, and external forces, which are forces exerted by some external object. The first internal forces we take into account is pressure. So this is the pressure. The first internal forces we take into account is pressure. Considering drinking from a straw, sucking at the end of a straw creates an area of low pressure, which forces the drink to move on the area of high pressure below to the area of lower pressure. This process is dependent on the change in pressures or the pressure gradient, which we can write as gradient of P. The second forces we factor in this friction or viscosity. If I pour water into a cup, the water moves quite fast. Whereas if I'm pouring honey, it moves quite slow. So this is because there's a lot more friction between the molecules of honey compared to the molecules of water. So the mathematical way of writing forces of Newtonian fluids is this one. And I'm going to go into depth as how these equations arises, but I have left a few resources you can use to read up about this. And finally, to account for the external forces, we just denote any external forces by the letter A. It's pretty common that gravity is the only external forces. So we sometimes write rho G, rho G here instead of F. And this is why the Navier-Stokes equations can model any fluid. There's simply two fundamentals law of physics written out for fluids. So why do these equations have $1 million prizes attached to them? Well, to answer that, just look at the actual problems for the Clay Math Institute. It goes as follows: to give reasonable leeway to solvers while retaining the heart of the problem. So we ask for a proof of one of the following four statements. Statement. The first two questions ask for a smooth solution to the Navier-Stokes equations. Let's break down what this means. When we say that a solution is smooth, mathematically it means that the solution is differentiable and chaotic. And chaotic doesn't mean that it's random. It simply means that it is, if I'm slightly change the initial condition, it results in a large change in the outcome. And this is why the question gets incredibly difficult. Sure, then if you Navier-Stokes equations, let us take some states of a fluid and let us predict what will happen in the future. But the chaotic nature of the fluids with turbulence makes it incredibly hard to make long-term prediction. This is why we can't predict the weather for more than 7 days. This is also why we can't predict when we are going to have turbulence on an airplane. Despite this, the Navier-Stokes equations are incredibly useful, and uh, they are they are used extensively to model aerodynamics objects. For example, a plane or car, like I mentioned before, the weather forecast also relies on the Navier-Stokes equations and still remains on one of the most important partial differential equations ever.